This is section 15.10 of Honors Algebra 2, Mutually Exclusive and Independent Events. Sounds like fun. Let's consider these sets. Set A is the elements 1, 2, 3, and 4. The set B is the elements 3, 4, 5, and 6. So just 4 numbers in each set. A union B, so this U symbol, but it's not quite a U, this U symbol is a union, is the union of sets A and B. So that's all of the elements of A combined with all of the elements of B. All of the elements that are in at least A or B. The union is going to be the set consisting of 1, 2, 3, 4, 5, and 6. We take all of the elements of A and combine them with the elements of B. I don't need to write the 3 and 4 twice because they are in the set. If they are in A, then they are in the union of A and B. So I don't need to write them again. All I'm noting is that they are in the set. This upside down U thing is called an intersection. A intersection B, A intersect B is the intersection of sets A and B. The intersection is only those elements that are in both A and B. So the intersection is both. We'll only take things that are in both. So the intersection here is what? 3 and 4. Very good. All of the elements that are in both A and B. So just the elements 3 and 4. Okay? So I've drawn this out in Venn diagrams here. A union B. A and B are both subsets of the whole numbers, the set of whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, and so on. So I've drawn that as my sort of overarching set. A and B are subsets of that, where A contains the numbers 1, 2, 3, and 4. That's the blue circle. Notice 1, 2, 3, and 4 are all in the blue circle. B is the numbers 3, 4, 5, and 6. All of them, again, in that green circle. But 3 and 4 are in both, so they lie in the intersection in this Venn diagram. So A union B is going to be any numbers that are in A or in B. So I'm shading A union B. I am shading all of A, and I am shading all of B. And that is A union B. And everything that's in one or the other. Now, A intersection B is only those things that are in both. So that is only the intersection in this Venn diagram. It's only the 3 and the 4 in the middle. Okay? Make sense? Good. If two sets have no elements in common, then the intersection of those two sets is called the empty set, written with this sort of 0 with a slash through it. And those sets are said to be disjoint. So if they have no elements in common, their intersection is empty. Their intersection is the empty set, and those sets are called disjoint. So let's take the set C of 1, 3, 5, 7, and 9, the set D of 2, 4, 6, 8, and 10. C union D is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Union is all of the elements combined. C intersect D, the intersection of C and D, is only those elements that are in C and D. What are they? There are none. So it is the empty set. The intersection of C and D is the empty set. So C and D are disjoint sets. They have no elements in common. Okay? Consider the situation of rolling a single 6-sided die. Let event A be rolling a number less than 3, and let event B be rolling an odd number. So then the sample space S can be represented by this Venn diagram. S, my options are 1, 2, 3, 4, 5, and 6. So that's S. All of those numbers lie in my Venn diagram somewhere. A is rolling a number less than 3. So A is the numbers 1 and 2. B is rolling an odd number, so B is the numbers 1, 3, and 5. A and B share the element 1, so that's in the middle. 4 and 6 are not in A or B. They are not odd numbers, and they are not less than 3. So 4 and 6 are still in my sample space. I can still roll a 4 when I'm rolling the die. But rolling a 4 is not achieving A or achieving B. So 4 is outside of A and B, as is 6, but they are still in the sample space S. So what is the probability of A? Well, A consists of 2 elements out of 6 possible elements, so 2 out of 6. What's the probability of B? Well, 3 out of 6. Okay? For any sample space S, the probability of the entire sample space is 1, and the probability of the intersection is 0. Because if I'm rolling a die, I have to get something in the sample space. I can't get 7 because there's no 7 on the die. If I'm rolling the die, I have to get something in the sample space. So the probability of getting the empty set is 0. I have to get something in S. Probability of getting something in S is 1, therefore, because I have to be getting something in S. So what is the probability of A union B? Well, A union B is anything that's in A or B. So that's 1, 2, 3, and 5. So that's 4 out of 6. What's the probability of A intersection B? That's only 1 out of 6. What's the probability of the set 4 and 6? Well, there are 2 elements in that set out of 6 possible elements, so 2 out of 6. Notice that the probability of 4 and 6 is 1 minus the probability of 1, 2, 3, and 5, which is the A union B. So the probability of 4, 6 is 1 minus the probability of A union B. 1 minus 4 over 6 is 6 over 6 minus 4 over 6, which is 2 over 6. That is useful to know. It's called a complement. The probability of a complement is, the probability of a set is 1 minus the probability of its complement. So the opposite occurring. We'll run across that again in a few minutes. Notice also that the probability of A union B, which we said is 4 over 6, well, 4 over 6 is equal to 2 over 6 plus 3 over 6 minus 1 over 6. Why would I break it up like that? Because 2 over 6 is the probability of A. 3 over 6 is the probability of B. 1 over 6 is the probability of A intersect B. So what we've said is the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. Which makes sense because A intersect B is being counted twice in A and in B. So if I'm finding the probability of A plus the probability of B, I'm doubly counting the things that are in the intersection. So I need to subtract one of those off of there so that I'm not counting them twice. That's all that this is saying. That 1 over 6 in my equation is the probability of getting that 1, while the probability of getting a 1 is included in the probability of getting the set A, and it's included in the probability of getting the set B. So I need to subtract one of those off of there so that I'm not counting the element 1 twice. Okay? Well, this is a very useful statement. For any two events, A and B, in a sample space, the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. So subtract off the intersections so that you're not counting those twice. That is incredibly useful. But what happens when two events have no elements in common? These events are called mutually exclusive, and they cannot both occur at the same time. So if they have no elements in common, then A intersect B is going to be the empty set. So the probability of A intersect B is going to be the probability of the empty set, which is 0. So that means that the probability of A union B is simply the probability of A plus the probability of B minus 0. Just applying my formula from above. So if I know that my events are mutually exclusive, if I know they cannot both occur at the same time, then all I have to do is add the probabilities because the intersection is 0, so there's nothing to subtract off. So if A and B are mutually exclusive events, if A union B equals the probability of A plus the probability of B. So for example, from a group of 10 seniors and 8 juniors, 3 students are to be selected at random to form a committee. What is the probability that at least 2 seniors are selected? Okay? Well, at least 2 seniors could occur in 2 different ways. I might have 2 seniors and 1 junior, and then I've got at least 2 seniors. Or I might have 3 seniors and no juniors. Those are my 2 options if I'm going to get at least 2 seniors. Okay, so we'll call this event of 2 seniors, 1 junior, event M. And we'll call the event of 3 seniors, event N. Now, event M and event N cannot both occur at the same time. I can't be picking 3 students, have 2 of them be seniors and 1 junior, and at the same time have all 3 of them be seniors. That makes no sense. They cannot occur both at the same time, so they are mutually exclusive. So the probability that I'm seeking, which is the probability of at least 2 seniors being selected, is the probability of M union N, which is the probability of M plus the probability of N. So we just need to find the probability of M and find the probability of N and then add them together. Well, the probability of M, probability of 2 seniors and 1 junior, is the number of ways that I can get 2 seniors, which is 10 things taken 2 at a time, the combination of 10 things chosen 2 at a time, times the probability of 1 junior, which is the combination of 8 things taken 1 at a time, divided by the total number of possible outcomes. So that is the combination of 10 plus 8 is 18 taken 3 at a time. So that's the way we calculate a probability. The number of ways I can get what I want divided by the number of total possible outcomes. So it's the number of ways I can get 2 seniors times the number of ways I can get 1 junior divided by the number of committees I can form. So that's 45 times 8 divided by 816. If you just work out the combinations, 45 times 8 is 360 divided by 816 simplifies to 15 over 34. That's the probability of M. Similarly, the probability of N, probability of 3 seniors. Well, that means I'm going to pick 3 seniors out of the 10, so that's a combination of 10 things taken 3 at a time, divided by the total number of possible outcomes, which is the combination of 18 things taken 3 at a time. So that is 120 on the top with the same 816 on the bottom. 120 over 816 reduces to 5 over 34. All right, so then the probability that I'm actually seeking, the probability of at least 2 seniors, is the probability of M union N, which is the probability of M, which is 15 over 34, plus the probability of N, which is 5 over 34. 15 over 34 plus 5 over 34 is 20 over 34. 20 over 34, of course, simplifies to 10 over 17. Now, 10 over 17 is approximately 0.588. So about 58.8% chance of at least 2 seniors being selected. We will write the probability, though, as 10 over 17, because that is an exact number, but sometimes it's useful to think of it as a percentage so we can get a handle on what the likelihood is. Consider the event of tossing a coin twice. Let A be the event of obtaining a head on the first toss, let B be the event of obtaining a head on the second toss. So my sample space is head, 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 tails, tails, head, tails, tails. 4 possible outcomes in my sample space. A, then, is the set consisting of 2 heads, so head on the first toss, head on the second toss, or head on the first toss, tail on the second toss. Notice the notation I've used to write those. Each set of parentheses is one event, or one item in the sample space. B is head, head, tails, head. So that is head on the second toss. So the probability of A is 2 out of 4. There are 2 things in A. There are 4 possible outcomes total in my sample space. Probability of B is also 2 out of 4. 2 things in B divided by 4 things in the sample space. Now the probability of A intersect B, well, the set A intersect B is one element. It is head on the first toss, head on the second toss. That is HH. So So the probability of A intersect B is 1 divided by 4. One element in the intersection divided by 4 things in the sample space. Are A and B mutually exclusive? Can they both occur at the same time? Well, yes, they do if I get a head on the first toss and a head on the second toss. So no, they are definitely not mutually exclusive. Are A and B independent? Well, we don't know what it means to be independent. So yes, they are independent, and here's why. If the occurrence of one event has no effect on the probability of another event, the two events are independent. So if one of them happening does not affect the probability of the other one happening, then they are said to be independent. Which makes sense here. Getting a head on the first toss does not affect the probability of getting a head on the second toss. Getting a head on the second toss is still a probability of 50%, a probability of 1/2, no matter what I got on the first toss. So these two things are independent. The fact that I get a head on the first toss does not affect the fact that I get a head on the second toss. The probability of getting a head on the second toss. So two events A and B are independent if and only if the probability of A intersect B equals the probability of A times the probability of B. Notice that's what we have here. 1/4 equals 2/4 times 2/4. Probability of A intersect B was 1 out of 4. Probability of A was 2 out of 4. The probability of B was 2 out of 4. 2 over 4 times 2 over 4 is 1/2 times 1/2, which is 1/4. So that is a way to verify that we have independence. All right. One last example. Based on past performances in the school band, the probability that Ryan will be selected to perform in the state band is 3/4, that Frank will be selected as 2/3, and that Charlie will be selected as 1/2. Suppose that the selection of one student does not affect another student's chances. Maybe all three of them play different instruments, so one of them being selected is not going to affect the probability of another one being selected. Find the probabilities of each of these events. First, that Ryan and Charlie are selected, but Frank is not, and then we'll find the probability that at least one of the three is selected. Okay. The fact that it says that the selection of one student does not affect another student's chances, that tells us that we have independent events. These things are independent because the probability of one happening does not affect the probability of the others. All right, so finding the probability that Ryan and Charlie are selected, but Frank is not, we'll call Ryan R, Charlie C, and Frank F. Those are my 3 events. So the probability of Ryan being selected, we're told that is 3/4. Probability of Charlie being selected is 1/2. We know the probability of Frank being selected is 2/3. But we want Frank not to be selected in this scenario. The probability of Frank not being selected is 1 minus the probability that Frank is selected. That goes back to what we noticed earlier. The probability of getting a 4 or a 6 was 1 minus the probability of getting a 1, 2, 3, or 5. So the probability of something happening is 1 minus the probability of the opposite of that happening. Probability of Frank not being selected, so the probability of not Frank is equal to 1 minus the probability of Frank being selected, which is 1 minus 2/3, which is 1/3. The probability of not Frank is 1/3. Okay, so if we want Ryan and Charlie to be selected, we're going to multiply their probabilities, and then we want Frank not to be selected, so we're going to multiply by the probability of Frank not being selected. So we'll take probability of R times the probability of C times the probability of not F, which is 3/4 times 1/2 times 1/3. 3/4 times 1/2 times 1/3 is 1/8. So the probability of Ryan and Charlie being selected but Frank not selected is 1/8. Now, the probability that at least one of the 3 is selected. Well, at least one of the 3, the probability of at least one is 1 minus the probability of the opposite thing happening. Well, the opposite of at least one is none. So the probability of at least one is 1 minus the probability of none. Anytime you see at least one in a problem, think of it like this. So if we can find the probability of none of them being selected, we'll take 1 minus that and we'll have the probability of at least one being selected. Otherwise, we'd have to think through all the different options of at least one. So let's find the probability of none. Well, the probability of none is going to be the probability of not R times the probability of not C times the probability of not F. Okay, well, probability of R was 3/4. The probability of not R is 1 minus 3/4, which is 1/4. Probability of C was 1/2, so the probability of not C is 1 minus 1/2, which is 1/2. Probability of not F is 1 minus the probability of F, so that is 1/3. So we've got 1 minus 1/2 times 1/4 times 1/2 times 1/3. 1/4 times 1/2 times 1/3 is 1/24. So this is 1 minus 1/24, which is 23/24. There's a very high probability that at least one of the three will be selected. 23 out of 24. Here are your immediate practice problems. Number 1, from a choice of 5 novels and 5 biographies, 3 books will be selected. What is the probability that at least 2 of those books are novels? This is like the seniors and juniors problem. Number 2, if the probability of event G is 0.75, what is the probability of G not occurring? So that should be a very simple, quick problem. That is the end of section 15.10.